15 minutes and give back the test 4, and we give a very quick review on the test 4. Now today we go to the Mohr circles, and here I rearrange the equations, and this is the equation for the normal stress in external direction, and this is the equation for the shear stress. And for this one, I simply move the average stress from the right hand side to left hand side to become like this. So given those information, if you look at carefully and say if we manipulate the information, if I take the square sum of the both equations, then the same thing on the right hand side, we take the square and then we take the little bit arrangement, and actually this one will become to r squared. In here, we have the average is the average of the normal stress. And again, this one is constant, and which means that one is equal to, doesn't matter which orientation you rotate to, that is always constant. And R is we defined last time, and this one is equal to sigma x minus sigma y squared plus tau xy squared. People found these good properties. So that means this nice equation actually is a circle, right? The circle in an coordinate system of the normal stress as the, for example, take the normal stress as the horizontal axis and the shear stress as the vertical axis. So basically here you can see the circle is centered at sigma average. So for example here the sigma average is here. And the radius of the circle equal to r. This is called a Mohr circle. And Mohr circles have, based upon the information we're given the, remember we are given the status of we are given the status of the stress. So based upon the given information, we'll be able to calculate the center of the circle and radius of the circle, and we can draw it. And here the center is always located on the sigma axis. Okay, so this is the first step to build up the circle. Then the second step to utilize the circle is this. So this is step 1. Draw the circle. And step 2 is based upon the given informations. The Mohr circle represent is all kinds of the scenarios for possibly transformed status of the stress. And the second step is we want to, on the Mohr circle, we want to locate the point, 2 points that represent the status of the given distribution of the stress. Okay, and that way we can do by this. Again, the Mohr circles are the collection of the points, and each point represents is the status of the stress on in one orientation. Okay, so that means here in the Mohr circle here is a point. It has a coordinate sigma and tau. Sigma and tau represent is the normal and shear stress at a certain orientation. So with this comprehension in mind, then we want to say, for given this specific information, we want to find out what is a point corresponding to on the Mohr circle. And the way it's doing is this. We pick up the status of the stress on this one. This is called the x-plane. We call this x-plane is because this plane, which is normal to the x direction, so we call this called the x-plane. On the x-plane, we have the distribution of the stress. One is the normal stress, sigma x. The other one is the strain stress, and tau xy. We simply place the stress components in such a coordinate system because we like to utilize this kind of coordinate system. And the first coordinate is normal, and second coordinate is the strain. So we replace the coordinate system like this. Okay. And in the similar way, we can do on this plane, it's called the y-plane. So y-plane has a normal to the y direction. It's called defined the y-plane. So on the y-plane, we have the representation of the stress. And again, the first coordinate is the normal stress, which is sigma y. The second one is tau xy. And here, let me give one example. So if we would have the given information x, y, like for example this is 10, and as we did last time, this is 4, and this is 6. So in the x-plane, we usually label using, in the x-plane, we have representation is 10 and 6. In the y-plane, we have the representation of the coordinates which is going to be used on the Mohr circle plane is 4 and 6. Very straightforward. Another example is this. Okay, for this example, let me make this one. This is a 10, and this is 4. And then here is 6. Okay, so for this one here, we have to kick in our sign conventions. This is the x-plane. On the x-plane, we have the coordinate. The first coordinate is the normal stress, and here is minus 10. Here we have to, using this example I show you, we have to consider the sign convention. And for this case, this is per our sign convention, this is minus 6. And the same thing in the y-plane. Then the first coordinate is normal stress minus 4. The second one is minus 6. Okay. So once we write down the coordinate which represent the x and y plane, that completely can be used to represent the status of the stress for the given stress element. Now with those coordinates in place, then we're going to map place the point on the Mohr circle. And on the Mohr circle, we use is this. In our textbook, it provides two methods to place the points on the circle. The first method is this. I write it down carefully. For the x-plane, the textbook simply labeled this point as the x point. In the textbook, the textbook simply uses y to label this point. So the same thing, this is x point, this is a y point. So we're going to label x and y points under the Mohr circle. So for the y point is this. Whatever the coordinate we have, we simply copy the information onto here. Whatever is positive or negative, we just copy the information to here. And for the x coordinate, that's a little bit different. For the x coordinate is this. Whatever the information we got it, we copy the normal stress to here. Then we have to use the inverse, not inverse, negative to whatever we got from the for the x point. So for example, for this point, to map to the Mohr circle, you should use 10 minus 6. So that means whatever you got for the shear stress component for x point, you simply get a negative, put a, how to say, negate that value, and then you put down to the Mohr circle. Why? And that we have to make the consistency. Okay, that's a way to do that in Mohr circle.
Is that like the reactionary force on the opposite side?
No, no, that's a rule. Yes.
So is x always on the bottom half?
No, not really. Later I will use an example to map the information.
Just to making sure, you can never have like a positive sigma x or sigma y without having a positive tau xy, right? Or can you
X
have,
and Y always
well, no, I'm not talking about the circle. I'm talking about like the
who knows? And we can use example to see. Okay, and here I just use, this is a rule. The rule, that means just try to memorize. Okay, but the reason why, and I'm going to explain to you quickly, I make something, and I'm going to explain that one very quickly. But here, right now, before I do the demonstration, we just memorize it. Okay, just memorize, and then give me a few minutes. This is the first approach. And so maybe using this way, we can, for the two examples, let me draw the circles so we can see what's happening. So for the first example here, let me draw this one again. XY, and this is 10, 4, 6. And let me speed up let me skip off the other drawing. So for this circle, we make the circle here, and this is sigma. The average for this one, we calculate the average equal to 4 plus 10 divided by 2 equal to 7. So here, from here to here is 7, and radius equal to 10 minus 4 divided by 2 squared plus 4 squared equal to 5. So radius equal to 5, and the center is 7. So here, from here, we can label the tau correctly. Yes?
Is it 4 squared or 6 squared for R?
Oh,
Sure.
yes. So that should be 3. This is 3, 4. Can I make 4? Allow me to make 4 because that'll be easy for my calculation. Are we okay?
Mm-hmm.
Okay, good. So the radius is 5, and the distance from the center to here is 7. So we know we have to label the tau axis to here. Okay. When you draw, you can draw by hand, but try your best to correctly label the distance. Okay. And now for this case, here we can see from here the x point representing the stress components on the x-plane. So that is 10 and 4. And y component is the status of the stress on here. That is the with coordinate 4 and 4. Okay, they both are positive per our sign convention. So now 10 and 4 per our sign. Then on the label, we have to label is using 10 and minus 4. Right? So that's our rule. So here is 7. So that means here in total to here is 12. So 10 probably is here. So this is our x. 10 minus 4 here. Okay. And then for y is 4 and 4. So 4 and 4, that will be probably here. Okay. So once you labeled, then if you label correctly, here is the check status is this. The 2 points linking together must form a diameter. Sorry. Okay. The connect X and Y, and to form a line that is the XY. So XY, which should be a diameter. If not, then your placement or your labeling of the 2 points are incorrect, and fix them. Okay. I will save this one and do another demonstration, but let me use this one.
Dr. Cheng,
yes.
When you say diameter, do you mean that they're 180 degrees or that they'll be the magnitude?
They'll always be 180 degrees.
180 degrees.
Yeah, separate.
Okay.
And how about let me use this side for the other demonstration. And the other example is this one. XY. And then this is 10, 4. And this is 4. Okay, so for this case here, the average equal to minus 10 minus 4 divided by 2 is minus 7. The radius is equal to minus 10 plus 4, 2 squared plus minus 4 squared, and that is equal to 5. So circle. And this is our normal stress. And here the average is minus 7. Okay, so the average measured from here is the 7 to the left. And then the radius is equal to 5. So that means here should be the tau axis. Okay, so here this point is to the left, so that will be minus 7. So now for this case, the x point is here. The stress is on this plane is minus 10, minus 4. And y is on this plane is minus 4 and minus 4. So now we label the y first, the minus 4, that would be about here. And then we label the x on which is whatever we got is minus 10, and we put a minus to what we obtained. So here should be equal to 4, right? So here is x, is minus 10 and 4. Again, you can check it. The 2 must be a diameter. The 2 must be diameter. That means the summation of the 2 points, the coordinates of the 2 points is such that the horizontal one must be equal to average. The vertical one must be equal to 0. And that is for the checking. Okay, that is the first approach provided by our textbook. The second approach to label correctly the x and y point onto the Mohr circle is this. Utilize this. I'm going to explain it quickly. So here on the tau axis, we simply added the 2 symbols. And here is the counterclockwise direction. The top is clockwise direction. I'm going to explain it, what that means. For this one, that means doesn't matter for any stress component on any plane. You can see right now we take x as one example. The shear stress on the x-plane has a tendency, the full shear stress is pointing upward, has a tendency to rotate this stress element about the origin in counterclockwise direction. One more time. For this point, this shear stress component has a tendency to rotate this stress component by counterclockwise. So here we label the shear stress has a tendency like this. For y, on the y-plane, the shear stress component 4 has a tendency to rotate this block about the center in clockwise direction. So this has such a symbol here. So that means with those symbols, that means here, this point should be in the quadrant corresponding to the lower one. Okay? And Y point for this example is on the top. This one exactly match the first approach we recommend be suggested by the textbook. And for this one, again, for the X point, we look at here, the X point, the shear stress 4 has a tendency to rotate clockwise. So here we label like this, okay? And then on the Y here we have the information like this. So here you can see the X should be on the X one is clockwise, so that one X is located on the upper portion. And my personal my preference is I like to use this one rather than the first approach, because that is more graphical and then easier for me at least. Okay, so either approach will be good, up to you.